Okay, hi. Good afternoon, everybody. Welcome to the ISL Colloquium. It's a real pleasure to invite an ISL alum back to do a seminar here. Devavrat Shah, the speaker, used to be a student in CS, first PhD in CS 7 years ago. And then he's now a professor at MIT and visiting us, doing some really fun stuff on ranking using pairwise comparisons. So don't ask for numbers, ask for comparisons. Right? You can tell us how that works.
Thanks, Yash, for organizing the seminar. So this talk is about one extremely simple and intuitive, at least I find it intuitive, algorithm which as input takes a bunch of comparisons between, say, objects of interest. So for example, let's say you have three objects, A, B, and C, and it might take inputs like A greater than B or A preferred over B, A preferred over C, B preferred over C, and so on. You might have contradictions, you might have repetitions, that's fine. We'll take this as inputs, and as output, it will produce scores associated with each item, which in turn would lead to ranking of the objects. And it's pretty, and like most pretty things, you got to see it to believe it. So I'll wait for that, for you to get convinced about that. I'll show you some experiments which seem to suggest the algorithm is nice. It's intuitive, so we are not really the first ones to come up with this algorithm. Variations of this algorithm were looked at by a bunch of other people over different years in different contexts. I'll point those things out. But when these things happen, you might ask questions, what is it really formally doing? And that's what I will spend, let's say, at least half of the talk explaining you. What is the precise mathematical problem that it's solving? And that will also suggest a variation, right? That is what suggested us a variation of algorithm which was important to tweak. It's minor. I'll point it out when we get there. And that will be what the talk will be about. Feel free to stop me at any point of time because I just want to convey you the algorithm and go and try it out in your context, use comparisons, and scoring too. But this is a good way to do it. Alright, so with that short introduction about the talk, let's start building the context. So I'm thinking of scenarios where you have a bunch of objects and you have partial preferences between the objects available, and your goal is to come up with ordering or scoring of the objects, and ideally you like to have global ranking. Okay, so that's what is one example. Sports, take cricket, teams play games over years or over months, and then there are pairwise outcomes. So India beats Australia, and then you do sort of, which happened of course recently, if you follow it. In which case, it will be a partial preference that is given to you. You have all sorts of partial preferences, and then you will come up with a ranking of activities. Similar things with ATP ranking and so on. Social recommendations in Yelp, users provide ratings for restaurants, and then based on these inputs, you want to come up with a ranking of restaurants. Very close to us, conferences, especially competitive conferences, not 45% acceptance rates, think of 8%. So you really want to accept very few papers, in which case you will figure out, you will ask good reviewers to give their inputs, and based on those inputs, which are partial preferences, you want to come up with ranking of papers, so that you can decide which papers to be accepted and which not. Or graduate admissions, I'm sure this will record perfectly because February and March, at least at MIT, and I'm sure it's the same. When we are really scrambling to figure out of so many students which to admit and which not to admit. So, in all of these things, we have partial preferences over objects of interest, and we want to come up with ranking. Now, if I want to come up with one algorithm, and then you look at these diverse sets of examples and say, well, but here are different ways in which preferences are exhibited. Sports win and losses. Social recommendation will be star data. Maybe conferences will get more elaborate and ask rating between 0 to 10. So these are all heterogeneous. I would say
star rating is same as scores.
Same as scores, but it's a little less refined than 5 stars, or even worse version would be like and dislike. So it's just finer versus. My point is that let's look at all of these things as pairwise comparisons. Like India beat Australia, as I said before, of course, it is pairwise comparison. So here are 2 Palo Alto restaurants I've picked, and I've tried both. And I'm going to provide my rating. Yes. This is 5 star and this is 4 star, and I'm sure a bunch of you, I'm sure Balaji would disagree with that. But this is more vegetarian friendly for me than otherwise. And then I will convert that into I like tamarind over this French restaurant. Now, and similarly, if this was a ranking paper that I had submitted to a conference and let's say some friendly reviewer gave us 10 out of 10 versus some other paper was given 5 out of 10, of course, our paper is better than that paper. But these are all hypothetical. Now, in this situation, you might say that, well, this is the context in which comparison makes sense, but here did we lose some information? Probably yes, and this is entirely debatable. But the other side of the debate that is worth considering is that humans are arbitrary in terms of providing their stars or ratings, right? And so your 4 star versus my 4 star is not clear, but your 4 star over your 3 star is same as my 5 star over my 3 star. That is my comparison there. And that's what I will stop. At the end of it, what we have is a situation where we have a bunch of objects. Over objects, we have a bunch of pairwise comparison data available. Let's have partial preference data. And given that input, what we're going to do is we're going to come up with a global ranking of objects. And we would like to have a global ranking of objects along with some scores associated because, I mean, there were times when Federer was better than Nadal in ATP ranking. And then there were other times when he was better than Nadal in ATP ranking. But then we know that there were times when he was extremely good compared to Nadal, and then there were times when he was not really that good. So we should have some scores to express those intensity also. Okay. And this is the problem that I want to solve. Right, so let's just look at one representation. I'm going to think of this problem as follows. Let's say I've got 6 objects and data which is pairwise comparison, and we'll think of that as a graph over 6 nodes with, in this case, since there's 6 nodes, there's 6 choose 2, which is 15 possible pairs. In this figure, I have shown 8 of them, which are compared. So think of 8 teams are played with each other. If you look at one cricket here and look at test match records, then this is likely to happen. What does these numbers represent? This number says that, well, Team A and Team B played this plus these many games, out of which these games were won by Team A and these games were won by Team B. So this is my data, and given this weighted graph, I want to come up with that. Okay, now if you are a tournament planner, or more specifically in the context of, let's say, graduate admissions, you might say, well, I've got different student applications coming in, and I can assign those student applications among professors subject to load constraints and so on, fairness and so on, in some forms so that they will lead to different type of data graphs or data collection. So for example, let's say these 2 students are assigned to Ben, then Ben could provide comparison between these 2 students. But he would not be able to provide comparison between 1 and 3 because, of course, he has not looked at the number 3. So depending on which students he gets, different types of comparison graph are constructed. Question is, if I had a choice, subject to constraint, what sorts of graph I should constrain so that in some sense I can get the most information out of it? So that will be the design question. So say, for example, there is at MIT there is a group which spends time building crowdsourcing platform led by Rob Miller. They have one such this precise problem that they're trying to solve, and the algorithms I'll describe you they're using there right now. What they try to do is that they want to sort items between which you want to obtain comparisons, But comparisons are subjective. Let's say I show you two colors and I ask you which color is better than the other color. Maybe I show you two shirts and say which shirt is better than the other shirt. In which case, if you want to sort things for using subjective input from users, and you want to get the best answers out with the least number of questions, it's precisely this type of question that we are trying to solve. So you can think of this as a crowdsourcing problem. Anyway, so the goal for me in this talk is to try to solve these two problems.
So, did you say how you quantify how good a solution is?
No, I have not told you. And that's in some sense vague. But I'm sort of, right now I'm trying to convey just intuitively that what I'm trying to do. Clearly I have not defined the question.
Well, maybe in terms of consistency, otherwise,
Great.
answers or something.
When we come to the model, in that context I'll define precisely what I mean by good, and then we'll quantify what sorts of graphs are good in that context. Any other question? Yes?
You can have violations of transitivity. It doesn't have to be that, A is better than B and B is better than C, then A is better than C. You might prefer C better than A. You know what I mean? So, but that doesn't, you don't have to have transitivity in this case?
No, so it's, in the beginning I said that the algorithm will take data, a bunch of pairwise comparisons, they may have contradictions. That is, somebody might say A greater than B, somebody might say B greater than A. That's absolutely fine. Okay, so I mean, in some sense, these are the questions that are raising the point that, okay, so how do we really sort of make sense of these questions? Okay, so if I want to put in pictures, here I've got data, and now I know what sorts of decision I want to make, but how do we even define what decisions I want to make, and how do I think about these things? So, well, we do what we do normally. And we say, well, I'm going to connect these data with decision to some meaningful model. In this case, I'll take help of a reasonable probabilistic model. And once I have that model, hopefully my questions will make sense. Once my questions make sense, hopefully I can come up with an optimal policy or algorithm to solve them. And once I look at that solution, I say, well, it doesn't make sense because I can't implement this for whatever reason. I'd like to come up with some approximation that I can implement. And the hope is that when I did this, at the end, I went from data to decision, with an intuitive algorithm, makes sense, and there's a justification that I got in the process. And in some sense, this is the path in which I'm going to explain the algorithm and the results. Of course, it's like a snake getting rid of its path. For us, the way process worked is we first came up with algorithm and then looked at the model and then we came up with a variation of it which worked. Alright, so that's what our plan would be. Before I dive into this, one might say, well, it sounds good, but only if it works. And this is the only example in which it works. For us, we have been reasonably successful in a bunch of examples, and I'll share some of them with you if you're interested. So one of the things we looked at was looking at sparse choice model to capture people's choices to solve what people call assortment optimization problem. This was with former student from here and colleague, friend at MIT, Vivek Farias, and our student Shrikant, who's not in my room. We looked at diffusion-based models for identifying agents in settings like Twitter. This was part of thesis of my former student, Devavrat Shah. We looked at crowdsourcing problems, not exactly of this class, but type of questions that are very nicely modeled by a model that came up in 1970s by David and Skeen. Came up in the context of the medical history collection. And using that, we have developed nice answers. We have colleague David Carter and Sylvan Begin, former student from ISL. And now it's going into this crowdsourcing platform called IQ. If you have not looked at it, it's an interesting game. It's run by our computational and neuroscience department. And what they're trying to do is that they've got a bunch of images of brain, and they're asking people's expert help to identify a few things. It's hard for me to explain without showing you what it is. But that sort of helps them to actually reconstruct a three-dimensional image of the brain. by looking at two-dimensional section. It's fun game. There's sort of 80,000 people playing that, and they're paying some of them money. So if you are good, you might get some money. And we're using some of these similar ideas for policy making for subsidy. It's with Tour Labs at MIT, which is led by Vijay Banerjee and Ashley Griswold. And we're going to see if this can help send rice packs to right people in Indonesia and around.
It's not power. I'm saying that.
See, for Porsche?
Yeah. But we started power, before that, I was like, cool, that.
Four has a four flag. But they're pretty rich. 9-second tolerance is poor. Anyways, it's poor. Alright, and this one is about rankings, so I'll talk about that. Okay, so again, I need to tell you the model, so that's where we can start building on it. Here's the model. I'm going to say that the ground truth is distribution or permutations. What does that mean? Let's say we've got those 6 objects and you've seen pairwise comparison. The way I will think that these pairwise comparisons are generated as follows. There's some ground truth over, some distribution over permutations over these pairs of objects. To generate every data point, I will choose a permutation at random first. And then between, let's say, 1 and 2 that I'm interested in, I will look at their order from that permutation, and I will produce that data. So for example, here's a caricature. Let's say these are the data points that I have observed. Let me imagine that they were effectively coming from this kind of permutation. So there was a permutation A, B, and C that was picked from ground truth, and I actually revealed only this. Now suppose this was actually the surrogate, then maybe this is one distribution that might actually be consistent with it. Yes, please.
Are you looking at drawing from the space of all possible permutations?
For the time being, let's say yes.
Oh, so no assumptions.
Yeah.
In big data, in big matrices, that becomes a little bit combinatorial, right?
Yeah, sure. So I mean, let's have 1,000 as a number. It's a reasonable number because there are 1,000 restaurants in Boston, so it's 1,000 factorial. I'm not pretending that I'll be able to solve that problem yet, but it's good to think about it. Okay, and let's say if that was the thing, by inspection, maybe this should be the ranking that we should be interested in. So now let's say, suppose we believe that this is a reasonable model and this is what we're going to execute. Then first question to ask is, let's say we figured out this distribution, how would we do rank aggregation? This is a classical rank aggregation problem, and it is, it's pretty hard. Let me just quickly capture the background of it. The rank aggregation problem is you're given you have a bunch of objects, and over objects you have, let's say, in classical ranked election setting, you will have 6 candidates, and you will have voters. Each voter will provide you ordering of all candidates. So here I'm showing you one ordering. Say candidate 2 is preferred over 3 and so on. Candidate 6 preferred over 2 and so on. Now, these are votes. You can think of votes in this case as a distribution of permutations. And given this, if you want to come up with one complete preference or ordering that satisfies certain sets of reasonable axioms, it's impossible to do that. And this was done by Gennaro, famous paper, in 51. So that means that this factor is hard to solve unless you start dropping some axioms or start going for something else. And one such algorithm that has been looked at extensively in literature is called Kamini optimal, where it says that I'm going to come up with an ordering as an answer which minimizes disagreements. What is disagreements? Let's say here is one candidate permutation, say 1 greater than 2 greater than so on. For that candidate, I'm going to find out how many disagreements does it have with my data. For example, suppose if these were 2 votes, then I will look at this vote and my candidate and compute for each pair of objects whether they agree or not. In this case, there will be 6 choose two. So it could be that it will disagree with all of them, or it could be that it disagrees with all of them. And there will be the number. And then I will add up those disagreements for each vote. And that will be my total disagreement. I will look at the guy which minimizes them. Okay. So it is, I'm trying to solve an optimization problem and factorial possibilities. And as expected, it is hard. You can't hope to solve it subject to appropriate hypothesis. Why was this actually very exciting for people who are in the field? Because it satisfies what people call the extended Condorcet criteria. What it translates, forgetting extended, say Condorcet criteria, this was proposed by Condorcet in 1780s, around that time, which effectively says that, let's say, suppose if I have a Condorcet winner, then my policy should find Condorcet winner as one of these beta. What is a Condorcet winner? Well, if data is such that there is one candidate, in pairwise comparisons, it wins over all other candidates, then it should be sort of there. Putting it other way, in our distributional setting, with respect to distribution over permutation, if there is one candidate I, such that probability of I greater than j is greater than half for all j, then it should be found as the winner by the algorithm. Okay? And if data is such that, then of course this algorithm will find it. Can't solve it, so people went for two approximations. It's a nice network flow-based algorithm. It's kind of solving max weight matching. But of course, what does two approximation have? Two approximation approximates that objective, and it doesn't mean anything. So let's look at some other algorithm. The Borda count. A Borda count is a very intuitive algorithm. It says that, look, here's what I'm going to do. For every candidate, I'm going to find its average position with respect to the distribution I have. So here, for example, if I have 2 votes each with probability half, the position of, let's say, 2 is 6 in this case, and position of 2 is 5 there. The average position 5.5. And so that guy gets pretty high score. And I will score candidates as per that. And that will be my winner. That is why it's useful as geometric property as shown by Young in the 70s. Effectively, it drops one of the edges from there. Now, the data that I have is pairwise comparison, not entire distribution. And if I were to think of these algorithms, well, since the way Kamine algorithm is defined, it only uses pairwise data. So I could use it if I wanted to. But again, what would I do with two approximations? What about Borda count? Can we try to compute average position of candidates from pairwise data? I mean, pairwise data I greater than j does not tell me anything about positions. It just says relative things. Here is something cute actually. What if I actually had precise distribution or marginal distribution of it? Is for every I and j, I knew precisely what is the probability that I is ranked greater than j. It's not going to happen, but let's just assume this. Then I would calculate scores like this. It's for every candidate I, or say Eij, summed over j. And I will use that as a score, and that's exactly Borda count.
So this way you do several repetitions of each variable.
Good. Many comparisons complete.
Yeah.
Maybe it's interesting. It's very simple, but it's effectively useless. There are lots of. I mean, this is an exciting question. So clearly, you expect usually literature on this. This book has chapter 9 as a nice summary of learning distribution over permutations. We'll read that, and then let's skip all this. Okay, so that's a background. Questions? So I started with question with data decision that with the model, which is distribution of permutations, and I convinced you that at least it's harder. Literature doesn't have solution. So that's a summary. What do people do practically? Well, maybe distribution or permutations are not arbitrary distributions; they are reasonable distributions. Maybe basically, they are the ones that were satisfying, that are consistent in some sense with the axioms that Young looked at to analyze the board account. And in that case, there would be effectively instances of what's called Thurston's model. And I will come to that in a second, but like, for example, multinomial logic model is used by net files in transportation systems. TrueSkill, which is a TrueSkill ranking system for online gaming in Microsoft, it uses a variation of this model. Pricing in applied industry or ELO rating in chess, all of them use some version of Thurston's model. So what I'm going to do is I'm going to restrict to this version of Thurston model, which is also called Bradley-Perry-Lewis model or MNL model. And as you can see from names, this is discovered at least 4 times independently. So what is a model? A model is a very simple parametric model. It says I've got for all n objects of my interest, I'm going to associate parameter with each one of them. And I will use these parameters to generate a distribution over permutation, or that will define my distribution over permutation. Let's think for a second that all w's are equal. Then we would expect that the corresponding distribution over permutation will be a uniform distribution. How do we generate distribution over uniform distribution over permutation, or sample a uniform permutation at random? We got n slots, first rank, second rank, nth rank. The way we will fill is as follows. I've got initially n items. I choose any one of them at random. Fill that in first position. Out of remaining n minus 1 items, again I choose something at random, put it in second position, and so on. The number of bits I used is log n minus 1, and so on. That's why I ended up using log n factorial or n log n bits. Pretty good procedure. Now let's sort of generalize that a bit. Then we'll get this model. So for each object I have w1, w2, wn. To fit the first slot, I will choose ith object with probability proportional to its parameter wi. Once I have fixed that, from the remaining, I will choose again proportional to their parameters and so on. If you wanted to implement this in your, let's say in Python or MATLAB, what do we do? So if you are an E person, what do we do? We will run exponential plots. Okay, so you have an exponential with parameter w1, w2, wn. Look at the first clock ticking. It will be ith clock with probability proportional to wn. So that's how we implement it. Alright, so that's the model. Okay. So if I know the parameters, I will know their scores of objects. That tells me their competence or their inherent goodness. And in some sense, if this is the model, then these are the scores that I would like to know. And the way we will sample for the purpose of explanation is, let's say we have a graph that is already determined. It says that these are the pairs which I'm going to, that it has edges, and for a given edge, this is the pair between which I'm going to, let's say, have some number of comparisons. And for simplicity, I'll say that for each pair corresponding to edge in the graph, I will choose k comparisons. Okay, so is the model clear? So n objects, given graph, some unknown parameters, and for each edge in the graph, I will choose k pairwise comparisons, and each time I is preferred j or j preferred I as per these probabilities. It's a useful exercise to see that the construction that I explained you of MNL leads to these pairwise margins. Okay, so here now I'll get it out. Algorithm I call it rank centrality for obvious reasons, as you see. So open up everything. So this is the graph. I'm going to define a random walk on this graph. The way I want to define random walk is as follows. My goal is to define a random walk such that its stationary distribution has higher value for a node which is higher scores. So let's say, let's assume that there are only two players. Let's say somebody else and I. And we've played lots of games, and that person has won most of the games. Now I want to define a Markov chain or random walk on two of us. How would I define it? Well, when random walk is on that person, because that person has won so many times against me, and since I want that person to have higher probability stationary distribution, that should jump to me less often compared to jumping from me to that person. Let's take the natural variation, natural concrete version of that. For any ij, I'm going to define probability of going from I to j is proportional to how often j defeats me. And I will normalize that by in a natural way. And this +1 is just think of Laplacian correction for sun rising, not rising. So you know this Laplacian thing, right? If I ask you a question, what is the chance that tomorrow's sun is not going to rise? And given that we know that the world has existed for n days, where n is a pretty large number, what would be your estimate? 1 over n, or 1 over n plus 1, because on day 1 you don't want to say it's 0. Right? Okay, so that's the probability, and of course we'll normalize it like this to make it a transition probability matrix. Yes, please.
What range of values for K on the last slide are you sort of thinking of exploring there? Are we looking at sort of one sample for each pair, or are we looking at like hundreds and hundreds of games played between any two individuals?
Definitely, more K I have, more information I have.
Yeah.
Depending on what K I have, will determine the errors that I will have. And we'll precisely talk about that in a second. Excellent question. Okay, so that's my probability transition matrix. And given the definition, as long as G is connected, I will have a unique stationary distribution for this random walk. And that stationary distribution or values will be my scores. Any question about algebra? And as I said, it's pretty intuitive and it is also semi-obvious. And that was the reason why also it had been in a variation was proposed by Dwarf and Sati. What they did not do is they did not normalize it. And actually, by not normalizing, you will see errors. And I will show you this.
The +1 and +2 there's no reversibility.
Actually, that analytically helps.
I don't even have that.
Yeah, but it's not as
Markov, no, question. I'm just asking.
Yes.
Markov is not reversible.
Markov chain is not reversible. And it will, even if I did not have it, will still not be reversible.
No, proportional to H it's all because it's in direction.
Arbitrary, yeah.
Direction matters.
Yeah.
No, because otherwise, I'm going to
Yes.
I'm right.
So in some sense, plus is, if there was, it actually helps. Because if you, let's say you and I play, then let's say you won 100 times, I won 0 times. And there is one. Yes, please.
so now this equation looks like H rank. Is there any connection?
Yeah, they are both Markov chains. And that's all that's the connection, right? Because PageRank has its own natural model that's telling that sort of why I should sort of, in some sense it's a natural random walk weighted by the degrees. It is in vanilla version. This is telling me that I have weights coming from pairs of, let's say, pairs of tournaments or pairs of games.
There's a long series of papers on the analytic hierarchy process. Is this the same Sati?
You mean the guy who sort of writes soft papers?
Well, there's written papers on variations of this kind of thing since like the 70s or something. And I'm wondering if this is distinct from all variations.
Yeah, so this one is distinct from all, and it took me a while to sort of actually figure out that there is actually a clean algorithm in that paper. So, I think it's the same set. I could be wrong because I know a few papers of him now, but a few constants will not matter, but in practice, with a bunch of data where we have played, where we knew the truth and we could tell the truth, one seemed like the reasonable thing to do. It's not a principle. Yeah.
Just one more thing. You said in your ground truth model, I noticed that the assumption is that in the ground truth there are no contradictions. It seems like you're giving a real numbered score to every item in advance and then using that to kind of generate the input data for the experiment. Are you also going to touch on data where the ground truth really does have contradictions, where A really is better than B, is better than C, is better than A?
Okay, so
like chess players, it's pretty common.
So what you're saying is not true, really, right? Because ground truth has parameters which are W1, W2, Wn, but really the ground truth is the distribution that is parameterized by those parameters. And distribution over permutations, even with given sets of parameters, will have support in this case over entire space of permutations. So every permutation A has some positive probability of being likely, some more than other, of course. It's a unimodal, and hence it's nicer. But it does have contradictions by definition. I mean, what would be more interesting, and I don't know how to answer that, and that makes it a big question, is what if I have a mixture of ML models? Let's say population is of 5 types, with 1/5 probability is of type 1, 1/5 type 2, and so on. Now what? How would you aggregate that?
It seems like if you have contradictions, like A better than B, better than C, better than A, then you do this, you just make it like uniform.
Sure. So in that case, if you say that data is such that I cannot distinguish them. Good question.
So, in a way, you could come up with a measure of how good an ordering is, because there might not be a good ordering, right? In this case, let's say something is ordered around a circle, you come out with, I don't find a good ordering. Is there a way we can get a metric that says how good your ordering is?
Putting it another way, how good are these scores separated from each other? That would be my answer. If its data is such that the scores are all equal, in this case I can't tell you anything. The data is such that the score is, let's say, 1 is unnormalized, 1, 2, 4, 8, 16, and I know it's pretty good already. Great. Any questions? All right, so now let's see, I have 15, 20 more minutes. 4, 5, 15, I can go. All right, so 20 more minutes I have time to tell you things. Before I jump into it, here's how roughly it would look. That score of I, and that is effectively score of J, weighted like this. That means that if I'm beating somebody with very high score, then my score will be boosted up. Or if I'm beating many with reasonable scores, again my score will be boosted up. If you compare it with the board account that I told you earlier, it would effectively look something like this, that my score is just this number. If you are doing power iteration to solve this equation, then this is what you would get if you started with uniform initial condition in the first iteration. So, in some sense, board account is just the first version of this iterative. Now let's look at some experiment. Is it doing something interesting? So given affinity to cricket, I took the cricket data. It's also available online. So here is a summary of let's say 16 teams. This is for what we call one-day international. So one variation of the game. This is data collected over the last 2 years. As per the ranking, International Cricket Control Board, ICC's ranking, England is ranked 1, South Africa 2, India 3, and so on. This is effectively summary data that, well, England won 35-23. algorithm trained with this data and produce these scores, and in fact these are the rankings. And I'm putting these rankings as per these scores. So you want to sort of just compare first six. That's pretty much fine. And this is in some sense you would expect, right? You always get top restaurants right in the city. It's always about the second tier one that the error happens. Let's see, which ones are major changes? This one and this one. Let's first look at this one. So it says Scotland played 15 matches, out of which won 9 and lost 6. Let's compare it with, let's say somebody like Kenya, who's ranked higher. Doesn't make sense. Because both of these teams effectively end up playing in the international tournaments where, like World Cup style tournament, not otherwise. So it's not like sort of these there are very different players. So there's something definitely wrong there. And maybe this is more likely than the other one. I don't know the control, neither you. Look at this one. Again, same thing. It's 17-15, 13-27. Doesn't make sense. And you can sort of go further with more detailed inspection analysis. In these rankings?
In ICC ranking.
So in ICC ranking, precisely.
Your algorithm the players matter. Your
Yes.
algorithm needs.
My algorithm precisely utilizes that because of the fixed point equation. The way ICC ranking precisely works is that for every game, there is some number of points which are uniform across all games are at stake. And the winner and loser gets some number of points depending on who wins and who loses. And tie sort of leads to board splitting. And that's what the official website says. It doesn't really describe the algorithm.
So you know the cross-validation test that you know, get to some comparisons and see how it works out.
You mean sort of take half of them and then sort of so we did uniform sampling of these things, and the algorithm is pretty robust in terms of producing it.
But could you
So we took the data,
for
we take
example,
half
take
of it.
ODI ranking from before some games are playing or something like that, and then compare that to your ranking system.
Okay, for this one, we did not do the time version. We did the uniform sampling version. I've got, let's say, 100 units of data. I'm going to take half of it and produce an answer. I'm going to take full of it and produce an answer. And it did not change.
No,
Ranking.
You use 2 years worth of data,
Correct.
but the seeds have been made even prior to that, right? Even the team properties are meant to be
Sure.
so by Scotland each one of them, it counts for a lot more.
There's a history.
That's right.
That's correct.
So the equilibrium where you're doing anyway is that you kind of agree, or just be this discuss. Discrepancy is huge because you just work on it, use what it is.
Sure, but I mean, I've really said this one, and I said this one. It's a reasonable contradiction.
No, I know Ireland's played some of these top teams. I don't think Scotland's played. Scotland are just beating Canada and Afghanistan.
What about these two? Okay. Anyways, this is subjective, so definitely you and I will debate. I can go back to the model and generate synthetic data, and then I will show you what the reality is. So here's what's happening. This is the logarithmic scale plot of the error, and this is the number of samples per edge. And what is the setting? The graph is Erdos-Renyi graph with the connected beyond threshold. What is the error? The error is ranking error weighted by the weights. So effectively, if I have item I and item j, and if I incorrectly rank them, but if the weights are too close, then it's not really a big penalty. but it should be a big penalty if the weights are different. And that's what we have done in weight difference and normalize appropriately. That's what's happening here. If you increase K, as you would expect, with maximum likelihood estimate to become better. With our algorithm, it also becomes better, and practically it's indistinguishable in these plots. If you don't have that normalization that I was telling you, and look at the Dwark or Sati's algorithm, which they call ratio metrics, plateaus after a while, so there is some issue there. If you use Borda count, then also it plateaus there. As you would expect. So this algorithm does get pretty good approximation of this. If I increase the degree, as this ratio goes to 1, effectively I'm getting complete graph. So with complete graph, as we have seen for large K, I would expect Borda count to get close to this. And that ratio matrix also get close to this. So if you have a lot of information, then most algorithms will do reasonably well. But if I have limited information, then algorithms will not.
Are you computing the maximum likelihood?
So with this model, it becomes a nice concave maximization problem. You can run a simple gradient algorithm. Interesting thing is that if you run gradient algorithm and if you look at its update, and you weigh them appropriately, let's say the updates you always have the step constant, right? If you choose the right type of step constant depending on where your state, then actually you will recover blind centrality. Which is, so maybe there is a reason why you do it very well.
Trivial that the maximum likelihood estimate is also than 1?
No. I'm just sort of plotting the maximum likelihood. Okay, now what can we formally prove? So here's what we can prove. So these are the actual parameters, and this is what we produce. The 2-norm error normalized this way is bounded above by this quantity. So of course, n is the number of items. K is per pairwise comparison, per pair how many comparisons we had. D is the degree of graph. I'm focusing on average degree of graph. I'm focusing on understanding graph model. And R is this discrepancy between the max and mean weight. Let's say if my weights are reasonably close, which is a pretty hard case to distinguish things, in which case this won't matter. But if you have a situation where the weights are pretty well separated, is 2 to the power n, 2 to the power n minus 1 kind of thing, this would be terrible. And one might ask the question, does this R deserve to be there? I don't think so it should be there. It's a weakness of our analysis technique. Because really the harder part is the one where weights are closer to each other, where discrepancies grow, not when things are separated. What sort of lower bound we can prove? Well, for this graph, of course we know that unless we have n log n samples, the graph in itself is not connected, so there is no hope of finding anything interesting. So, up to dependence on n, this is the best you can do. But in general, what can you get? Here's the type of bound you will get that this should be lower bounded by some universal constant, yet lower bounded by square root of q. This scaling is the right one. I believe it's not not too hard, not executable. But you can shave off this log n by looking at random regular graph rather than that's not really issue. It's the art of the issue. Yes.
Can you just make a brief comment about the fifth exponent there? I mean,
Why fifth exponent?
yeah, it's just not too common to see something like that.
So we must have
Y
done-
cubed just not enough. You
We
know?
must have done too many calculations.
Yeah. Is it something that comes from like an analytic proof, or is it just something that works in itself?
So this is byproduct of a bunch of lemmas that we have. It's hard to say if there is an intuition associated with number five.
So there's a cube over there, a square over there.
It actually goes by 5 by 2 square. if I had general graph, not adversarial graph? So if I have any connected graph, then the error is essentially same as before with these two additional things. This is variation in degrees. Let's forget that for a second. It's this part that matters most in our mind, and that is the spectral gap of Laplacian of the graph that we have. And how would I define that? Well, let's say I have a graph. I want to do, I'm doing a natural random walk on it, like phase rank, like randomly. At a given node, I jump to any one of it, my neighbor uniformly at random. Look at that Markov chain, look at its mixing time or relaxation time. That inverse will determine, or that will determine my error. If I had a line graph of comparisons, it would be terrible. I don't want that. Okay. And that means that if I had a graph choice subject to constraints, what I would like to do is I would like to choose one that minimizes this, which means maximizes that. And since the type of, since I'm trying to do this for Laplacian, this is primarily a semi-definite group. So if I had a setting available, I could solve it in principle.
Sorry, what is the number of samples in that version?
Okay, so number of samples are, because I've got n nodes, okay, and per node, number of edges are d. So effectively I've got order n d edges. Per edge I've got k samples, so order n k. The question? Alright, so if this is the answer to the second question that we had earlier. How would I choose the remaining 7 minutes? I'll give you a quick remark on proof why this is working, and then I'll tell you one place where we have used it. Any questions before I proceed? All norms are it. Okay, so here's the thing. Let's look at the original matrix P. I removed the plus correction one just for simplicity. So effectively the transition probability was how often the other person wins, normalized by how many times you have taken. And that was normalized by 50. Now, this itself may not be a reversible matrix because of the random nature of it. Thank you. Not reversible. This is the right one. But if you look at the expected value, in particular you replace age by their expected value, then they will be proportional to the W's. In particular, this will be proportional to this. And this is precisely the model. This is how the MNL model is set up. The fraction of time I wins over J is, or sorry, J wins over I is WJ or WI plus W. Now, if we had this as a matrix, not that, then this is what is a reversible matrix. That is, it will have numbers pi1, pi2, pi_n, such that when I looked at for any ij, pi I times p twiddle ij is equal to pi twiddle j times p to I. And the solution of that is this one, anyway. And in this case, as we know, this is precisely the station distribution. So that means that if I had the this expected matrix, everything would be good. Problem is that I don't have an expected matrix, I have some error around. And so if we go to just basic analysis, effectively what we'll get is that the right answer, versus what the answer we have, is that error is effectively captured as this. There's an error in expected answer, which is the ideal one, and what we observe. And then do a bunch of bounds, and you get the answer. I won't go into the details because of lack of time. I'll be happy to talk to you offline on papers and I'll tell you where we have used.
Right. I don't need to.
Yes.
If you have enough samples, that's why I get lots and lots of samples, and
infinite samples.
You get it exactly. The spectral gap. So you're saying I'm sampling edges from the weights. I'm going to sample some number of edges, but we take in proportion to those weights. And then it's one way. Stop some point and the rest of it.
Yeah, and in some sense, the spectral gap of peak middle is coming in because peak middle is close enough to P in this sense. So effectively, this is, let's say, a surrogate for spectral gap of P, because P is the matrix that I'm using to iterate to get to the fixed point of, or get the stationary distribution of P. If I'm thinking of running an, okay, depending on how you view it, if I'm running power iteration algorithm, then if I have an error at one point that will get diffused or get expanded, that's very effective this. And that's why this is. Okay, so here's what we did. We used it in this year's MIT graduate admission systems in our department. That means that in 2018, if you guys are looking to hire some graduate students, just be blind and take the best one from MIT. We also used in a bunch of conferences, and we're trying to put up the software for download hopefully by the end of summer. It doesn't have any library requirement other than basic Python library, which comes with most of the math. So hopefully you don't need to worry too much about it. And there are a bunch of polls that you can create. Maybe instead of Google, you can use this. Maybe Netflix will use this. Let me show you sort of how the RMI system works, and later you guys can tell me how your system works. So this is a very nice system that is actually built, in-house built and maintained by Franz Koschek and Robert Morris, two of my colleagues. They worked very hard for this. Roughly it looks like this. As a professor, I log in, anonymized it, and hence I'm not showing you online version, instead of screenshots. I log in, here's my first page. Says that these many folders are assigned, these many folders you've reviewed, bunch of options or recent queries, and bunch of history. Like, for example, I know how was Saki's letter for this student last year, and did we admit that student or not? So Saki's rated, for example, for that. Pretty high. And now the new version looks like this, that there were, let's say, some students, some professors have read, and this is highest ranking, lowest ranking, these are settings, and that's it. This is my personal ranking based on the inputs I have provided. Traditionally, we used to provide star rating to students between 1 to 4 star, 1 star, 2 star, 3 star, 4 star. And now we are asking them also to produce comparisons. So we could take both star and then comparison and produce personal ranking. This is global ranking. And let's say I look at these two and say, maybe Caltech person is better. Maybe. And so I'll drag this bar down, put these two people up, and then I will submit this button, and then I'll change this. This is roughly how things work. And of course, this is not used to make the final decision. This serves as an advisory in our last round of thing. But it cleans up a lot of personal communications that were going between people. All right, so with that, let me end the talk by saying that comparison is a good thing to do. Yeah.
Should we expect this to work better than they were last like it?
Now the question is sort of, do you believe in the model, right? As in, if you believe in the model, it's going to work as good as maximum likelihood, as shown by my simulation. The question is that, is it going to, in real data, is it going to do something better than instead of running this, running maximum likelihood?
Why do you say it's better maximum likelihood?
Well, for one, it's a simpler operation. The maximum likelihood I have to solve an optimization problem. So you got me to run 380,000. I will run into the offer and actually convert these questions. will